Hey guys, 12 and 14 have the exact same trick thrown to them. And both number 12 and number 14, when you have two different Pythagorean, or excuse me, two different trigonometric things, one of them squared and the next one is not, what you want to do, especially if it looks like it might be an identity, rewrite whatever the higher degree one is in terms of the lesser degree. I have a sine squared and a cosine, which means I'm going to use the identity of sine squared plus cosine squared is 1. Because sine squared then is 1 minus cosine squared. That's what you do with this style problem. Whether it is 2 sine squared x plus 5 cosine, if this was 2 cosine squared plus 5 sine, I would do the same thing, but I would rewrite in terms of sine, just by moving the cosine sign. Okay? This is the trick, this is the whole idea of why we learned and talked about Pythagorean identities, because you can do this trick. Whether it's a tangent squared with a secant, a cosecant, or cotangent squared with a cosecant, same rules apply. You need to know your identity, because that's really the only thing out of the verify, simplify stuff that we use all the time, aside from the reciprocal ones, and those are pretty simple. Okay? So when I use this one, if I use this, I get 2 times the quantity 1 minus cosine squared x plus 5 cosine x plus 1 is 0. Distribute through. And now I'm going to move everything from the left hand to the right hand side because I want to factor this with the leading term coefficient that is positive. Okay? So I get positive 2 cosine squared x minus 5 cosine x. And then when I added the 2 and the 1, I get positive 3, but then when I move it, I get negative 3. Very good. And now I'm at the factoring portion of the problem. 2 times negative 3 is? 6. Negative 6. What times what is negative 6 that you add together to get negative 5?
Negative and 1.
Those numbers. Yo!
Okay, I did it where you read on the other side and then you factor out a cosine and then you don't know. Just
So you said 2. Ooh, that's ugly. Don't you?
Yeah.
Don't you?
but that's a way to do it though.
Yeah, it's awful. Factor out your GCFs then. So you have 2 cosine x. You're left with a cosine x minus 3 plus 1 and a cosine x. Again, I've got both parts within the parentheses that are the same. So I didn't take that one out and rewrite it down. Cosine of x minus 3 is 0. And 2 cosine x plus 1 is 0. So this is what angle has a cosine value of 3. Is that possible?
No.
No.
It doesn't work.
Doesn't work. Cosine is bounded by 1 and negative 1. You cannot, there is no solution for that. All right. On the other one, I get what angle has a cosine at negative 1/2. And that one we can do. Is it a 30, a 60, a 90? Which one is it?
36.
It's the 60. Cosine is negative in the second and the third quadrant, so I come up 60 degrees, so I'll be at 2 pi over 3. I go down pi over 3, I'm at 4 pi over 3.
Right.
And I think this was just list all, I believe. Was this a list all or was it on the interval?
On the interval.
On the interval, so it was just listed, yes. Not, I'm sorry, general or list all, so this should be good. I'm going to try to keep talking as long as I can and see how long we keep Mika's hand in the air. Nice! What's up?
Did you
No, yes,
justify
maybe.
-1 by the whole thing to get the negative 2 cosine squared to be a positive 2 cosine.
Yeah. I basically moved it all to the right side and just kept the 0. Just flip-flop it around. That's all. Same trick goes for number 12. Does that make sense for 12 then?
I need to see it.
It's the same thing. Rewrite sine squared as cosine as 1 minus cosine.
What if I'm like cosine?
Or whichever. I thought that was a squared one.
Yeah, it is.
Oh my
is.
god.
Yeah, you're right. What else you got?
On 12.
It's the same thing.
Oh.
Why would it negative 2 cosine squared work?
You can't. Whenever I've done factoring, I always factor with my leading term coefficient positive. That way I don't mess up my signs. That's all. You're going to get the same answer if you do it right. Well, that's why we try to keep it positive. All right. What else do you want to look at?
You have a question?
Oh, I thought you had a wait, go back on this one. Yeah, Jonathan, what do you got?
How did you get the 2 cosine x get cosine minus 3?
What do these guys have in common? I factored it out.
Wait, but then wouldn't this still be a 3 cosine?
Where? Here? Oh no, think of it this way. Think of this as 2x squared minus 6x plus x minus 3. What do they have in common? It's just that our x value has a cosine attached to it. That's all. That's why sometimes it's all right if you switch to that u, use that u substitution, it's just a little bit cleaner. What else we got, guys?
Thanks. I feel like there's a middle.
Number 8.
I'm assuming the other 8.
On B.
What do they have in common?
Sine squared.
A cos.
Oh. I don't even know.
It is kind of fun.
Oh my god.
So if you factor out the cosine, I'm only doing it because you hate it.
Wait, I don't
If we inverse cosecant, you get sine. You inverse 0, you get undefined. Will you ever get sine undefined? Secant is the inverse of which function? Cosine. So this is what angle has a cosine of a half?
Wait, no, that's 60.
First and fourth.
What did you ask me?
And whenever I see cosecant written out, I think of CSX trains because my kids love trains. Thomas is annoying. He's pompous. If you listen to Thomas and how he's a little pompous little guy.
His name was Sir Thomas.
Sir Top Hat. Now I will say if you understand comedians and you know who oh God, what's his name?
Chris Farley.
No, the other dead guy. The 7 words you can't say on TV. George Carlin, yes. George Carlin was one of the original announcers, the narrators of Thomas the Train. So George Carlin did the background, the overwriting. He did it. Alec Baldwin did it. Ringo did it. So some of the ones you hear with like Alec Baldwin, some of the really old ones, they're kind of cool because like claymation stuff. Same thing with the Ringo, because it's a Beatle, so it's kind of cool. But the really, really old ones, when you have George Carlin doing it, because if you know any of George Carlin's stand-up, and he's reciting children's stories, it's just kind of funny.
Have you ever watched like America's Got Talent?
No.
Well, there's like this, like I don't know how old he was, but like he was a comedian and he got a stutter, but like he still wanted to be a comedian, and
Yeah.
it's so funny.
So the last little bit, guys, the last little bit of this trig stuff is the graphing. Now, we have done everything else that we need to do. We're not going to worry about half angle, double angle, or any of that stuff. You'll learn about that next year. What we're going to do is look at the graphs of sines and cosines today. We'll probably have a little bit of time to talk about the shifted sine and cosine today, which I know we will because we don't have an intruder drill going on. Tomorrow we'll talk about all the shifted of sine and cosine. Then on Thursday we'll do the tangent graphs. Tangent graphs and their shifts. That means Friday, it depends on how everything goes with all the shifting thing. Maybe Friday I might show you a shortcut on some of the shifting, or we might just go right to the reciprocal properties. It's all depending on how things work. I might wait for the shortcut just for the reciprocal because there's a lot going on with those. Anyway, we know that when we're graphing sine and cosine, and you guys have seen this a little bit so far, is that everything that we've done has been built off of the unit circle. And we talked about the amount of time it takes to go around the circle. We talk about the revolution of the circle. As you're going around something and coming back to where it starts, you're starting it over and over again. So it has what's called a periodicity. It repeats itself. There's a specific period to take to go through one cycle of the circle. The cycle of the circle is 2 pi. It goes around 360 degrees, so the period of the circle would be 2 pi revolution. As we go through this, and if I'm looking at just the sine values, we know that sine values mirror the y coordinates. And as you go through the unit circle, we get the 4 quadrantals, which are very easy to mark up. And we return back to 1 and 0. If we take the revolution of the circle and we plot it into a 2-dimensional plane where we're looking at the y values of how high up and down it goes over the course of its x coordinates, you get something like this. We know sine starts at 0. It cycles itself through, which means it finishes at 2 pi. Halfway between 0 and 2 pi is pi. Halfway between pi and 0 is pi over 2. And halfway in here is 3 pi over 2. It's convenient that it works with our quadrantals. Go figure, that's why we learn about them. So if you look at just the ordered pairs on the quadrantals for the sine value, sine starts at 0. When it gets to pi over 2, it's equal to 1. As it comes back to 0, goes to -1, and comes back to 0. So it looks like this. It has that wave to it. It's a sine wave. It's a sound wave, if you want to think even further into it. What you're able to do with this off the unit circle is this is just a basic single period sine value. It has an amplitude, the height at which it goes, of 1. It's positive, so it starts positive and rotates itself through. What we're going to do is throw in different values to it, like an A value and a B value, and eventually an H and a K, to stretch it to a higher amplitude, widen it, or condense it to a different period. So whether it's a longer period to rotate through or a shorter period. The frequency, if you will. Think of sound waves. The higher the frequency, the shorter the period is, the higher the peak, so it rotates itself through faster. Yes, sir?
Would those A and B values be like the domain and range?
Very similar. Yeah, very similar. Very similar. Now, the domain, you're going to have certain boundaries for obviously your domain. Your domain will be like your A value, your plus or minus A value. Your range is, we're only going to be graphing these within 1 revolution. Sine and cosine, as it goes all the way throughout, it just repeats itself. There's no boundary to it. Whereas tangent graphs have the asymptote because you can't divide by 0. So we're going to have little things like that, but we're only going to worry about 1 revolution. Pre-calc, we do multiple revolutions here. There's enough going on we don't need to worry about. Okay. So let me show you guys what's going to happen. You're going to get generic functions. Oh, wait, let me do a cosine real fast. Same thing here with cosine. If I'm on that same graph, that little t graph that I drew out there, where does cosine start when it's at 0? starts at 1, and then it rotates itself through. If you want to think about it, isn't cosine sine shifted left 90 degrees? Watch. If I shift sine graph 90 degrees over, I'm at a cosine graph. If I shift cosine 90 degrees the other way, I'm at a sine graph. Okay. The differences between sine and cosine in their graphs is that sine, for what we're going to call a parent function today, is always going to start at the origin, whereas a cosine graph is always going to start at its amplitude, its a value, whether that a is positive or negative. It always starts there. And you come up with these very simple rules. We're going to get the equations. Y equals a sine of bx, and y equals a cosine bx. Where the a's and the b's help us to determine amplitude, how high up and down things go, what direction they're going first, and the b value allows us to figure out the period. How fast does it take to cycle through one revolution? Okay? And it works really, really easy. And I know I say things are easy, you guys all don't believe me. I know, but believe it or not, third hour kind of believed me today. Yes, sir? And this, how fast does it go through? How long does it take to get there? The distance it takes. It depends. You have a shift to it. It's a scalar. It's a scalar that you're throwing into it.
So but if it's a circle, wouldn't A be the same in scaling it?
I see where you're going with that. You'll see what happens here. It's a simple formula to show you because you have sine of x and cosine of x are your generics. You're multiplying it by something to raise it up and down, or how fast something is repeating. That's all it's. It's if there are two different scalars that are being put into a function.
So would it not be a circle if the square was not equal?
It still is, because if you divide it out, you still get to get the circle.
But if you change it to the main form, A would be the radius and B would be the circumference, so they'd have to scale equally.
Well, that's how scale factor works.
So if they didn't scale equally, then it would be a circle.
You're worrying too much. I see where you're going. I wouldn't worry so much about that. This is, you'll see how this thing's working through, okay? So you have two things you have to worry about. Your A value, it tells you how high up and low the graph goes. It also tells you direction to start. The B value is used to calculate the period for both sine and cosine. They both have the same formula for finding that. How fast? And how low can you go? It's supposed to be how low. So what happens then is that we're going to take a graph and we're going to figure out its amplitude. The amplitude is always going to be the absolute value of A. Amplitude. How high up or how low it goes. All right. The period is always going to be defined by 2 pi divided by the absolute value of B. We throw the absolute value in there for B for now because later on in pre-calc when you have a negative B, you'll know what to do. You won't see a negative B in algebra 2, but that is the generic formula. So the reason that we talk about amplitude being an absolute value is that your A values can be negative. Let me just look at the slide with that. Oh.
Same.
What's up with his head?
There's only one.
Wait,
Yeah,
did
His eyes are pointing on the side graph.
Yeah, it looks like Gilbert.
No. Yes.
Gilbert on the body.
So you get this. So we look at this following graph. Let's try this. It's very easy to work yourself through. We say y equals 2 sine of 4x. Here's what we do. I haven't bothered this yet. If I want to do this, what I always start these graphs with, whether it's a sine, cosine, tangent, shifted, non-shifted, reciprocal property, whatever, I'm always going to start the problem the same way. I'm going to list what A is, what B is. Tomorrow we'll talk about H and K, and then we'll figure out amplitude and period. My A value here is 2. My B value is 4. From that, I write down my amplitude. Well, my amplitude is 2. My period then is going to be 2 pi over 4, otherwise known as pi over 2. From that, I know everything that I need to do to start my graph. So what I do is I make a T-chart sideways. And I will suggest that you make these larger than what you think you need to, because the easier it is to find the breakpoints for the curve, the easier it is to write out your ordered pairs, the easier it will be to do the shifting, all of that. Make them bigger than what you think you normally would. It really does help to visualize it a lot easier, all right? Especially with the fractions. Yeah. So I know that sine starts at 0. I'll write that down again. Sine starts at cosine starts at the A value. Okay. Sine starts at 0, it goes to the A value. Cosine starts at the A value, then goes to 0. So if your A value is positive, then sine would go from 0 up. If your A value is negative, sine would go from 0 down. If cosine has an A value that's positive, it starts at that positive, works way down to 0. If it starts at a negative A, it starts at the bottom, works its way up. That's the only differences between the positives and negatives in this case. So what we do is we know that sine's going to start at the origin, and it's going to finish one cycle out here at pi over 2. Now, when you start worrying about your other breakpoints, leave pi out of it. What's half of a half? A fourth. What's half of a fourth?
8.
So do you agree that you're going from 0, 1/8, 2/8, 3/8, 4/8? Usually when you start working with the fractions, it gets to be that simple. You take half of your endpoint, there's your middle, half of your middle, there's your first breakpoint, and then add it back over. Okay? And you add it back over. It's so people freak out when they see all these fractions. It's very quick.
Those fractions could get out of hand easily.
They can. They really can. Because you can get some really crazy, nutty period values if you really wanted to. Okay. What was our A value? 2. So this one here, I go up 2 and I go down 2. Sine starts at 0. Where does it go? So it goes up to 2, down to 0, down to negative 2, and back to 0. There's your curve. They were asking about this earlier today is, what do I do with those ordered pairs? Well, today I'm not really worried about listing them out, but tomorrow it's going to be a good idea to remember to write out your ordered pairs for your parent function. Because as you go through these, if you know that you're going to have some shift of some H and K, H goes with the horizontal, the X, K goes with the vertical, the Y. So you can add in X plus your H, y plus your y, or y plus your k if you needed to. So you can take these ordered pairs and just add them around before you place them back in. It's really, really clean to do it this way. Not so terrible yet?
Heck
Yeah.
Sir?
Yeah, so is this T graph, is this like a line graph?
Yeah.
Not like- okay,
Yeah, that's all it is. It's just a line graph. It's just a sideways T. I think it's just cleaner if I say it that way, because I don't want you guys to use graph paper. I want you guys to scale it and do it on your own, because it's more visual if you give yourself the space that you're denoting, okay, this is going to be pi, because I don't care if pi over 2 is marked where 2 pi is going to be, where 10 pi is going to be. Who cares? If the breakpoints are written right, that's all that matters. You're just making it visual, okay? Yes, sir.
Right. So, I know we probably wouldn't graph anything like this, but is there a way to like tilt the graph? Like angle it?
No.
Like, okay.
Is this go up there, then go up to 2 because the amplitude?
Yes. It goes 0 to A, 0, opposite A, 0.
So A is not the radius, right?
That's scalar. It's just multiplying it by taking the sign graph, multiplying it by 2. Try another one.
Wait, Mr. Murphy,
Yes, sir.
how does this line graph tie into the full circle with cross quadrant thing?
The quadrantals are your generic parts of the function itself, and that gives you the parent function, if you will. The 0, 1, 0, negative 1, and 0.
Right.
And then to that, you're multiplying some scales. You're multiplying, you're raising the amplitude up, you're multiplying it down the other way, you're changing direction. You're changing where the breakpoints go by multiplying by some other scalar b. That's all that a's and b's do.
So inverse of sine, cosine, and tangent that can't go on the opposite side of the graph. Because you know we had the.
Because they blow themselves up. Yeah, they blow themselves
So
up.
that's the inverse that you can solve. You can solve the sine.
Yes.
Okay.
So in this one here, I've got negative 4 cosine of x over 8. So I write it out. My a value, and I know you're not watching videos on your phone.
Me? No, I'm doing calculator stuff.
Am I doing calculator stuff?
Sorry.
So do you think you need to be doing calculator stuff? Do you think you're going to get a calculator? No, so writing this out the long way would probably be a good idea.
Graphing pictures.
Yeah, well, let's worry about these graphs. These are pictures too. What's that? Well, people start complaining about not being able to figure things out because they're, pissing away other things doing other stuff in class. If you have problems with the way I approach stuff, just ask me later. You don't have to mark about it later during class, though. Okay. Anyway, you walk through it again the same way. My a value is negative, but what's my amplitude? It's still 4. My period is going to be 2 pi over 1/8. So what's your period? 16 pi. Okay? Yes, sir. Multiply by the reciprocal. It's going to end at 16 pi. It's going to start at 0. It's going to go up to 4. It's going to go down to negative 4. Well, it's going to at least, it's going to start over here. It's somewhere it's going to have some 0. I meant to say it like that. So what's half of 16? What's half of that? What's the other breakpoint?
Wait, how do you find the
Half of 16 is 8. Half of 8 is 4. Add that back to 8 and you get the middle.
Oh, you're adding 4 to 8.
Yeah, or you can think of it this way. If you know your endpoint is 16, you can multiply it by 1/4, 1/2, 3/4. You get all your points. Works same way. In this one here, you get your A value is -4. It's cosine, so where is it going to start? -4. Goes to 0, goes up to 4, and goes back to 0. Cosine graphs always start at the A, whatever your A value is, whether it's positive or negative, and then it goes to the next point.
Does it not matter at all whether it is positive or negative?
It just tells you the direction of the graph. That's all. It's reflecting it over the axis, is what it's doing.
Wait. Oh, so if it were positive, then it would be positive instead of positive?
Yeah.
Okay.
Yes, sir.
For today, is the cosine, it's like the middle of the number, or the second number, is that always the highest point or lowest point?
Yeah, and I'm going to get to that. What happens with these graphs? You're going to have maximums and minimums within the period. Cosine is going to have it can have at most one maximum or at most one minimum because of the way it works. But it can have two. All right, it depends on the values of A. If you're looking within certain things, we're not going to really concern ourselves so much with maximum and minimums in these things. We don't see it, the need for it all that often. You might get it on like a word problem, but that's something very easy just to figure out within a certain range. You use type of graph. Yes, sir.
So why did we do 14.3 and 14.4 before this stuff?
Because 14.3 and 14.4 had to use all of the inverse functions that we were already working on. So once we figured out what angle has cosine of 1/2 and all that, we solved the equations that uses it. And then then I went back to that was the practical of the first part of 14.4. Learning about Pythagorean identities allowed us to do that 2 cosine squared plus sine squared plus sine equals 0. It allowed us to do that next part of the equation. Graphing gets kind of thrown in there. You can do the graphing really at any point after you start understanding how the unit circle works itself through. I've taught it this way for a couple of years, and I thought that the flow of it seems to be easier because if you don't have the background on the unit circle and how things relate to one another, graphing's a pain. But if you understand why things are rotating through, it's okay. That's all it is. It's just I don't do it different. I do it different than other people, but in my mind it makes sense. In my mind it's weird. Let's try it over. Just for fun, since we're running a little ahead of schedule here, DeJounte just gave me the look.
Yeah. If Trump becomes president, or like gets rid of Common Core, is he going to like go to the book things?
Mr. Murphy will get to show us rad triggers.
Wait, is this Common Core? I thought Common Core was only for younger.
There's
I thought Common Core was for
Bless you.
elementary school.
There's a lot of it for everything. Yeah. Anyway, so here's what happens. You get the functions that look like this. I'm just gonna show a little bit of it real quick. It's actually really easy.
This is going to be on the homework.
I don't know. I might give you one. So what happens with this? What happens with this is that you're going to do basically the exact same thing as graphing the sine as a parent graph, but then you're going to move it left and right, up and down. Now, if it says x minus h, what does that mean that I'm going to do with the h value that's in the parentheses? Opposite. Very good. If it says plus k, it's the same. Okay. So what I would do is I'd do the same thing. A is 3, b is 2, h is pi, and k is 4. Which means this is going to go right pi and up 4. What's my amplitude? My period is pi. So when you go to graph something like this, you do the exact same thing. Now, here's where thinking about where you're going to go later on in the graph will allow you to adjust that t-chart that you make. You might move it a little bit further to the right. You might lower that value down some. Since I know I have to go up 4, I might do that. So I've got more room up top. And I know that I'm going to move my period right pi. I might just start my first period here because I'm going to have to add all one over. See what I'm saying with that? I'm just getting the idea of like, okay, things are going to move a little, so I'm going to make it a little over, I'm making it over exaggerate where it's going to wind up. So I still do the same thing. I'm going to go up 3, I'm going to go down 3. It's a sine graph, so I know it's going to start at 0, end at pi, pi over 2, half, oops, half of that, and 3/4 of that. So I'm going to go up, down, and up. To each of those points, I have to move them to the right pi and up 4.
Right.
Which means I'm going to have to add in
Wait,
more points to the right. So I start at my end point, and what's pi plus pi? And then I do a reset of my points here. That's really all it is. Because now, bless you, now my new starting point is going to be at pi, because that's where the period's going to start itself, and it's going to end at 2 pi then. That's all we're doing. It's a really, really simple thing to do. It's just a matter of rewriting out your breakpoints. So let's see, 3 pi over 2, 5 pi, oh, this is 5 pi over 4, and this is 7 pi over 4. It's going to go all the way up to 7, and it'll go all the way up to 1. So instead of being at 0, it's going to be at 4. Move to 7, go back to 4, to negative or to positive 1, and back to 4. And there's our shift. That's it, guys. It's a matter of just taking your first set of ordered pairs and then just moving them over by resetting your period. And then towards the end of the week, we'll do this. Which means you graph this and then you just blow it up. Yes, sir.
Why did we decide the period was 2 pi over 2?
The b value was the period. Every time you find a period for a sine or a cosine graph, it's always going to be 2 pi over b. Our b value is 2.
Oh, so it just happened to.
Yeah. I wanted to do one real fast. I didn't want to make the fractions really nasty.
Right.
Bless you. Yes, sir. I'm probably going to try and go for Wednesday. That way, if people are sick on that Wednesday, you still have Thursday to make it up, because Lord knows you don't want to take it after you come back from spring break.
Okay. Oh, the Lord, no. It's on the calendar.
It's on your sick calendar?
Yeah.
It's already planned. So on 14.1, forgot which problems I had you guys do.
You can actually just.
Do these, please. The first 3 are identify the amplitude and period. The next 4 are graphs. The last 2 are write the equation given the amplitude and the period.
Easy, that's easy.
So think about it. If you're given the period, what do you have to solve for? B. If you're given the amplitude, you'll know what to go. Yes, sir. And in this case, it's going to say it's A and B are positive. We don't worry about negative b's in here. Well, we could because there are co-function identities, but we're not going to do it.
And there's imaginary tricks.
Yeah. Oh yeah. By the way, I forgot that there really is such a thing as imaginary trig. I just chose to forget it. There is trigonometry on the complex plane. We do look at that in pre-calc. I just haven't taught that section yet, so I forgot about it. Yes, ma'am.
Do we have to graph them too?
Yeah, there's just four. The four in the middle are the graphing ones. These four are the graphs. The other four are, the other five are identifying some parts or writing in an equation. I didn't want to do too many graphs. It's going to be graphing a lot.
32, 33, 41, 44 right now.
Yeah, the middle four are the graphing ones. It tells you to graph it.
Alright.
Okay? So remember, when you're graphing it, guys, list out what A is, what B is, what's your amplitude, what's your period, and just go from there. Survive sitting. You could have walked around. Would have been all right.
Probably.